Welcome to The Explainer. Today, we're slicing right into the anatomy of the right-angled triangle and completely demystifying the math behind it. If you've ever stared at these shapes and felt just a little bit overwhelmed by the formulas, you are absolutely in the right place. Triangles are basically the hidden building blocks of our physical world, right? From the architecture of massive suspension bridges down to the digital rendering of your favorite video games, they are literally everywhere. So we're going to break down exactly how they work, why they behave the way they do, and give you the geometric superpowers needed to really understand them.
And here's our roadmap for today. We'll be decoding trigonometry, exploring the anatomy of right-angled triangles, meeting the constant hypotenuse, looking at the reference angle effect, and finally, mastering the famous Pythagorean theorem. We'll just move through this step by step to build a complete picture. All right, let's dive right in with our first stop, decoding trigonometry.
People often hear the word trigonometry and immediately tense up. It sounds like this incredibly complex, intimidating subject reserved for, advanced mathematicians. But the word itself, it literally just means the measurement of triangles. That's it. It derives directly from the ancient Greek words trigono, meaning three or angle, and metron, which means measurement. There is absolutely nothing to be intimidated by here, for sure. It's just the study of three-sided shapes. Once you grasp these basic measurements, the entire subject naturally just opens right up to you.
Which brings us to Section 2, the anatomy of right-angled triangles.
To really get a handle on our mathematical specimen today, we first have to ask ourselves a pretty fundamental question. What exactly makes a triangle right-angled? What actually separates this specific geometric shape from any other three-sided figure you might just quickly doodle on a piece of paper? Take a second to think about what that defining characteristic truly is. Well, the answer is remarkably simple, but absolutely uncompromising. To be a right-angled triangle, the shape has to possess exactly one 90-degree angle. No more, no less. That perfectly squared-off corner is literally the foundational DNA of our shape. If that 90-degree angle isn't there, you're dealing with an entirely different kind of triangle, and the rules we're about to go over simply won't apply in the same way.
So, let's look at the basic rules governing the shape. Every single triangle is just a figure made of three straight lines. But there's an unbreakable law in geometry here. You gotta think of every triangle as having a strict geometric budget of exactly 180 degrees for its inside angles. It can never exceed this budget, and it can never fall short. And because our right-angled triangle has already claimed exactly 90 of those degrees for its defining corner, that means the remaining two angles are forced to share the remaining 90 degrees. They just have to split whatever is left in that budget between them. Okay, let's move on to part 3, the constant hypotenuse. Now it's time to meet the first major character in our triangle anatomy. I actually like to call this one the constant boss. Meet the hypotenuse. This is the absolute longest side of any right-angled triangle. It proudly stretches right across the shape, bridging the wide gap between the two shorter sides and just locking the entire geometric structure perfectly into place. And what's really fascinating here is that the hypotenuse is our constant anchor. Imagine taking this triangle in your mind and spinning it around, flipping it upside down, tossing it across the room. No matter how you rotate the shape, the hypotenuse fiercely protects its identity. It's always located directly opposite that 90-degree angle. It is definitively the longest side of the triangle every single time. It is completely constant and never alters its identity. And that's great for us because it makes it your ultimate easy-to-spot landmark whenever you're navigating these geometric problems. But here's where things get interesting. Let's look at Section 4, the reference angle effect. So here is where we hit a fantastic mathematical plot twist that introduces our two shape-shifting characters. But to understand these shapeshifters, we first have to understand the reference angle. The reference angle is just the specific angle you choose to focus on, out of those two remaining acute angles we talked about earlier that are sharing that leftover 90-degree budget. Now, why does this matter? Well, because without choosing a reference angle, the rest of the triangle's identity remains completely locked in mystery. Picking this angle is an absolutely crucial, required step before you can figure out the true identities of the other two sides. Let me illustrate the difference between those remaining two sides once you've picked your angle. Imagine yourself standing exactly at your chosen reference angle. If you look straight across the triangle, right in front of you, that side is your perpendicular. Now look down at the floor your angle is resting on, situated perfectly in between your reference angle and the 90-degree right angle. That, my friends, is your base. So the really crucial point is this.
If you change your mind, walk over and select the other acute angle as your reference angle, your perpendicular and base will literally swap identities. They act like complete shapeshifters, depending entirely on your perspective. The boss, our constant hypotenuse, never moves and never changes, but these other two sides, they're locked in a constant dance of swapping roles. One moment, a side is the perpendicular, and from another point of view, it immediately becomes the base. Because of this shape-shifting nature, identifying these sides just becomes a simple, fail-proof 4-step algorithmic process. Step 1, find your 90-degree right angle. Step 2, look directly across from it to spot your constant hypotenuse. Step 3, pick your reference angle. And step 4, map out your shape-shifting base and perpendicular based solely on that reference angle. Seriously, if you follow these 4 steps in this exact order, you will never get lost, no matter how complicated the math might seem at first glance. Let's actually put this into practice with a hypothetical triangle ABC. Imagine angle B is our 90-degree angle, which obviously makes side AC our constant hypotenuse opposite it. Now, if we mark angle C as our chosen reference angle, can you guess where the perpendicular is? I want you to pause for a second and really think about it based on the rules we just went over. Okay, following our logic, the perpendicular must be the side exactly opposite our viewpoint at C, which means it has to be side AB. And the base, the side trapped right between our reference angle C and our 90-degree angle B, is side BC. Easy, right? Let's bring it all together in our final section, mastering the Pythagorean theorem. Now that we've isolated our 3 main characters, the constant hypotenuse, the shape-shifting perpendicular, and the base, let's look at the unbreakable law of geometric nature that binds them all together forever. Enter Pythagoras' theorem. This legendary theorem states that the square of the hypotenuse is always equal to the sum of the squares of the remaining 2 sides. You really have to give that the gravitas it deserves, because it isn't just some random rule in a textbook. It is an incredible mathematical reality that dictates how space itself is structured. And that brings us to the elegant, unbreakable formula of the right-angled triangle. Hypotenuse squared equals perpendicular squared plus base squared, universally known as h squared equals p squared plus b squared. It's honestly amazing how such incredibly complex geometric relationships across the entire universe boil down to something so beautifully concise. This simple little equation is the absolute engine that drives basic trigonometry. But why does this matter for you? Well, because these 3 sides are strictly mathematically bound by this equation, it builds your practical toolkit. It means you are never truly stuck. If you're missing a piece of the puzzle, this formula lets you reverse engineer the truth and find exactly what the shapeshifters are hiding. Need the perpendicular? You calculate p equals the square root of h squared minus b squared. Need the base? It's b equals the square root of h squared minus p squared. You now have the ultimate power to solve for the unknown. To wrap up our explainer today, I want to leave you with this final thought to ponder. If you measure a triangle and you run those numbers through Pythagoras' formula, and that elegant equation of h squared equals p squared plus b squared does not perfectly mathematically hold true, is your triangle truly right-angled? The answer is a definitive no. This formula is essentially the ultimate polygraph test for the shape. If the math doesn't balance perfectly, the shape is an imposter. Keep that unbreakable geometric reality in mind next time you spot a right angle out in the real world. Thanks so much for joining me for this explainer today.